What if I told you that one fuel pump modification, completely invisible to the naked eye, gave one racer an illegal advantage worth 3 straight championship seasons? This is the story of how Warren Hines, the Professor Johnson, outsmarted the entire NHRA with a secret so simple, yet so brilliant, that when competitors finally discovered it, they couldn't believe they'd been beaten by something hiding in plain sight. And picture this. It's 1985, and pro stock drag racing is experiencing its golden age. These aren't your typical street machines. We're talking about 500 cubic inch monsters producing over 800 horsepower, naturally aspirated, running on gasoline, not nitromethane. The competition is fierce, the technology is cutting edge, and every team is searching for that extra tenth of a second that separates winners from also-rans. At the starting line sits a silver Oldsmobile Cutlass, its engine silent, but ready to unleash hell. Behind the wheel is Warren Johnson, a former General Motors engineer from Virginia who relocated to Arizona and earned the nickname Warren the Professor E for his methodical, scientific approach to racing. What his competitors don't know is that buried deep inside his engine's fuel system is a modification so clever, so undetectable, that it will give him a power advantage for the next 3 years. And this is the story of how one man's understanding of fluid dynamics and fuel flow turned a standard Hilborn mechanical fuel injection pump into a secret weapon that flowed 200 gallons per hour, 40% more than anyone thought possible from that size pump. It's a tale of engineering brilliance, competitive secrecy, and how sometimes the biggest advantages come from the smallest modifications. Bonch. To understand the genius of Johnson's trick, we need to travel back to the early 1980s pro stock scene. The class was undergoing a technological revolution. Gone were the days when a talented driver with a well-built engine could compete at the top level. This was now a game of incremental improvements, where success was measured in thousandths of seconds and fractions of a percentage point in efficiency. The rules were strict: 500 cubic inches maximum displacement, carburetors or mechanical fuel injection only, gasoline fuel, and minimum weight requirements that meant every component had to earn its place. The Hilborn fuel injection system was the gold standard for pro stock racing. Unlike the electronic fuel injection systems we know today, these were purely mechanical marvels. A belt-driven pump pushed fuel through precision machine nozzles directly into each cylinder's intake port. No computers, no sensors, just mechanical perfection. The pumps were works of art, aluminum housings containing rotating barrels that created fuel pressure through centrifugal force and precise tolerances. Every pro stock team ran them because they offered superior fuel distribution compared to carburetors. The pump's size was critical: too small, and you couldn't feed enough fuel to support maximum power; too large, and you added unnecessary weight and packaging problems in an already cramped engine bay. Here's where it gets interesting. Every team assumed they were getting maximum flow from their Hilborn pumps. After all, these were precision-manufactured racing components built to exacting specifications. The pump bodies were regularly inspected by NHRA technical officials who checked external dimensions, mounting points, and drive ratios. What they didn't check, what nobody even thought to check, were the internal fuel passages. And Warren Johnson saw what others missed. With his engineering background from GM, where he'd worked on production engine development, Johnson understood fluid dynamics at a level most racers didn't. He knew that fuel flow wasn't just about pump size or pressure, it was about the entire system's ability to move liquid efficiently. Every restriction, every sharp edge, every undersized passage was a bottleneck that limited power potential. The problem Johnson identified was beautifully simple. The Hilborn pumps, despite their racing pedigree, were originally designed for much lower horsepower applications. As pro stock engines evolved from 650 horsepower to 750, then 800 and beyond, the fuel system requirements increased dramatically. An 800 horsepower engine running at 8,500 RPM needs approximately 400 pounds of fuel per hour. That's about 65 gallons per hour at wide open throttle. But that's average flow. Peak instantaneous flow during the injection pulse could be much higher. The standard Hilborn pump could theoretically support this, but only if every part of the system was optimized. And Don Johnson's solution was elegant in its simplicity. Working in his Arizona shop, away from the prying eyes of competitors, he carefully disassembled his Hilborn pumps. Using precision measuring tools, he mapped every internal passage, every junction, every potential restriction point. What he found confirmed his suspicions. The internal passages were sized for the pump's original design flow rate, not for the extreme demands of modern pro stock racing. The modification process required exceptional skill. Johnson carefully enlarged specific internal passages using specialized porting tools. This wasn't random grinding. Each modification was calculated to improve flow while maintaining the pump's structural integrity and pressure capabilities. The inlet passages were opened up to reduce restriction on the suction side. The transfer ports between the pump chambers were enlarged to allow smoother fuel movement. The outlet passages leading to the distribution block were carefully radiused to eliminate turbulence. Nantium. But here's the genius part. All these modifications were completely internal. From the outside, Johnson's pumps looked absolutely stock. Same casting numbers, same external dimensions, same mounting configuration. An NHRA tech inspector could examine these pumps all day long and never spot the difference. Even if a competitor got their hands on one, unless they completely disassembled it and knew exactly what to look for, the modifications would go unnoticed. Naturally, the results were staggering. Johnson's modified pumps could flow 200 gallons per hour, a full 40% more than a stock pump of the same size. This wasn't just about raw fuel volume. The increased flow meant Johnson could run larger injection nozzles without dropping fuel pressure. He could maintain optimal air-fuel ratios at higher RPM where other teams were going lean. Most importantly, he could do all this with a compact pump that didn't require special mounting or drive modifications that would attract attention. To put this advantage in perspective, let's talk numbers. In pro stock racing, a 1% power advantage translates to roughly 0.03 of a second in the quarter mile. Johnson's fuel system modifications were worth an estimated 15 to 20 horsepower, about 2 to 3% more power than his competitors. That's nearly 1/10 of a second advantage, an eternity in pro stock, where races are often decided by thousandths. Once in the 1985 season was Johnson's coming-out party. Racing his silver Oldsmobile Cutlass, he dominated in a way that had competitors scratching their heads. His consistency was remarkable, not just winning races, but setting records and running numbers that seemed impossible for the cubic inches and weight he was carrying. Other teams dynoed their engines and couldn't understand how Johnson was making so much power. They assumed he had better cylinder heads, a superior camshaft, or some exotic coating or treatment. Nobody suspected the fuel pump. And here's what made Johnson's advantage even more devastating. In pro stock, teams share certain suppliers and technical information. Cylinder head specialists, camshaft grinders, and machine shops often work with multiple teams. Secrets are hard to keep when everyone uses the same vendors, but Johnson did his pump modifications himself, in his own shop, telling no one. This wasn't a purchased advantage. It was earned through understanding and craftsmanship. The technical beauty of Johnson's modification extended beyond just flow volume. By improving the pump's efficiency, he reduced parasitic power loss. Fuel pumps are driven off the engine, and any restriction in the pump requires more power to overcome. Johnson's free-flowing pump actually required less horsepower to drive while delivering more fuel. It was a double win, more fuel delivery with less power consumption. NHRA. The 1986 season progressed. Johnson continued his dominance. But now teams were getting suspicious. They noticed his consistency at high RPM, where their engines would start to lay over. Johnson's would keep pulling. At first, they suspected illegal fuel. NHRA tested his gas repeatedly. It was legal. They checked his engine displacement. Legal. Weight. Legal. Every external dimension and specification checked out perfectly. The frustration in the pits was palpable. Here was Johnson, Rutledge the professor, methodically destroying the competition with what appeared to be the same equipment everyone else had. Teams spent fortunes trying to duplicate his power. They bought identical Hilborn pumps, had them blueprinted, matched every external specification. Still, they came up short. The answer was right there, hidden inside a component nobody thought to question, and Johnson's fuel system advantage allowed him to explore other areas of performance. With adequate fuel delivery guaranteed, he could be more aggressive with compression ratios and ignition timing. He could run leaner mixtures during cruise conditions for better throttle response, knowing he had the fuel reserve for full power. Every aspect of his engine calibration could be optimized because the fuel system was never a limiting factor. The psychological impact on competitors was significant. In drag racing, confidence is crucial. When you know your equipment is inferior, it affects your driving, your reaction times, your entire program. Johnson's competitors were spending sleepless nights and countless dollars chasing a ghost. They were looking for exotic solutions when the answer was a few thousandths of an inch of additional material removed from passages they never thought to examine. And by 1987, Johnson was virtually untouchable. He won the NHRA Pro Stock Championship, and his performance advantage was becoming embarrassing for other professional teams. The sport was supposed to be about competition, but Johnson had found a loophole that made competition nearly impossible. Still, his secret remained safe. The culture of pro stock racing meant that teams guarded their advantages jealously, and Johnson was the master of secrecy. The revelation finally came through an unexpected source. A former Johnson crew member, either through a slip of the tongue or intentional disclosure, mentioned the pump modifications to another team. The racing grapevine is efficient, and within weeks, every top pro stock team knew about the internal passage modifications. The rush to modify pumps was immediate and frantic. But here's where Johnson's true genius showed. Even when teams learned about the modifications, they didn't know the exact specifications, how much material to remove, from which passages, at what angles. Johnson had spent months perfecting his modifications, and simply knowing about them didn't mean competitors could duplicate them immediately. Many teams actually hurt their performance initially by removing too much material or modifying the wrong areas. The NHRA found themselves in a difficult position. Johnson hadn't technically broken any rules. The rule book specified external pump dimensions and prohibited certain modifications, but internal passage sizing wasn't addressed. To ban the modification would require admitting they'd missed something obvious for 3 years. Instead, they chose to quietly update the technical specifications for the following season, requiring stock internal dimensions or explicitly approved modifications. The impact of Johnson's innovation extended far beyond his own success. Fuel system suppliers began offering afresh modified SWI pumps with improved internal flow characteristics. What started as one man's secret became industry standard. Today's mechanical fuel injection systems all incorporate the lessons learned from Johnson's modifications: larger passages, smoother transitions, optimized flow paths. And in the technical specifications of Johnson's engines during this period were impressive even by today's standards. His 500 cubic inch Oldsmobile engines were producing between 820 and 840 horsepower at 8,500 RPM. That's 1.68 horsepower per cubic inch from a naturally aspirated engine running on gasoline. The compression ratios were extreme, between 14:1 and 15:1, requiring carefully formulated race gas to prevent detonation. The Hilborn pump itself was a marvel of engineering even in stock form. The pump body was CNC machined from billet aluminum with tolerances measured in 10,000ths of an inch. The internal rotating assembly consisted of a shaft-driven barrel with precisely machined vanes that created fuel pressure through centrifugal force. Operating pressure ranged from 100 to 200 psi depending on engine speed, with instantaneous pressures during injection events potentially exceeding 300 psi. Anthony Johnson's modifications focused on three critical areas. First, the inlet passage from the fuel supply line to the pump chamber. Stock diameter was approximately 0.500 inches. Johnson enlarged this to nearly 0.625 inches, reducing inlet restriction by almost 50%. Second, the transfer passages between pump stages. These were opened from 0.375 inches to 0.437 inches, improving flow between chambers. Third, the outlet passages to the distribution block. These were not just enlarged, but carefully radiused to eliminate sharp edges that caused turbulence and cavitation. The machining process required exceptional skill. Too aggressive with the porting tools, and you'd break through into adjacent passages or weaken the pump housing. The aluminum was soft enough to cut easily, but hard enough that maintaining precise dimensions required constant tool changes and measurement. Johnson used a combination of carbide burrs, grinding stones, and hand files to achieve the exact profiles he wanted. Lantern testing was conducted on Johnson's own engine dynamometer, a sophisticated setup that allowed him to measure not just peak power, but power curves, fuel flow rates, and exhaust gas temperatures across the entire RPM range. He could simulate race conditions, including the rapid throttle transitions and high RPM operation that exposed fuel system limitations. Each modification was tested individually and in combination, building a database of what worked and what didn't. And the economic impact of Johnson's advantage was substantial. In professional drag racing, prize money and sponsorship deals depend on success. Johnson's domination during those 3 seasons earned him hundreds of thousands of dollars in prize money and millions in sponsorship value. His competitors, meanwhile, were spending fortunes trying to catch up, money that could have been spent on other developments if they'd known where the advantage really lay. The ethics of Johnson's secret raise interesting questions about competition and innovation. Was it wrong to hide such an advantage? From one perspective, Johnson was simply better at understanding the rules and finding opportunities within them. He didn't cheat, he innovated. From another perspective, the spirit of competition suggests that such fundamental advantages should be shared or regulated to maintain competitive balance. The story also highlights the importance of systems thinking in engineering. Most racers focused on the obvious components, cylinder heads, camshafts, pistons. Johnson understood that an engine is a complete system where every component affects the others. A restriction in fuel flow doesn't just limit power, it affects combustion efficiency, heat generation, and component longevity. By solving the fuel flow limitation, Johnson improved his entire engine package, and modern pro stock racing has learned from Johnson's example. Today's rulebooks are far more comprehensive, specifying not just external dimensions, but internal specifications for many components. Technical inspection includes sophisticated measurement tools and even industrial CT scanning to detect hidden modifications. The cat-and-mouse game continues, but the mice have gotten much smarter. And the Hilborn fuel injection system itself has evolved significantly since Johnson's era. Modern versions incorporate his flow improvements as standard, along with additional refinements like variable injection timing and improved atomization. Electronic fuel injection has largely replaced mechanical systems in most racing applications, but Pro Stock still maintains its mechanical injection tradition, a nod to the purity of the category. Warren Johnson's career continued successfully long after his pump secret was revealed. He went on to win multiple championships and became one of the most respected engine builders and tuners in drag racing history. His nickname, Aufdowns the Professor, was well-earned. He approached racing as an engineering challenge, solving problems through analysis and innovation rather than trial and error. The lessons from Johnson's fuel pump modification extend beyond racing. In any competitive environment, the biggest advantages often come from questioning assumptions. Everyone assumed the Hilborn pumps were optimized because they were purpose-built racing components. Johnson questioned that assumption and found opportunity where others saw limitation. As the modification technique itself has become a standard practice in many forms of motorsport. Porting Y, the practice of enlarging and smoothing internal passages, is now common not just in fuel systems, but in intake manifolds, cylinder heads, and exhaust systems. The tools and techniques Johnson pioneered in his Arizona shop are now taught in technical schools and used in professional race shops worldwide. And while the secrecy surrounding racing innovations remains intense. Teams today use encryption, non-disclosure agreements, and even disinformation to protect their advantages. Johnson's 3-year run with his secret pump modification seems almost quaint compared to today's security measures, but it remains one of the longest-held successful secrets in professional racing history. Yet, for young engineers and racers, Johnson's story offers valuable lessons. First, understand the fundamentals. Johnson's GM engineering background gave him the theoretical knowledge to identify the problem. Second, question everything. Just because something is standard doesn't mean it's optimal. Third, test methodically. Johnson didn't just randomly modify pumps, he tested each change systematically. Fourth, protect your advantages. In competitive environments, information is power. The technical legacy of Johnson's modifications continues today. Flow bench testing, once rare in fuel system development, is now standard practice. Computational fluid dynamics software allows engineers to simulate fuel flow through passages before cutting metal. What Johnson discovered through intuition and experimentation can now be predicted through computer modeling. But perhaps the most important legacy is the reminder that racing, at its core, is about problem solving. The fastest car doesn't always have the biggest engine or the most exotic materials. Sometimes it's the car with the cleverest solution to a problem nobody else recognized. Warren Johnson recognized that problem, solved it elegantly, and dominated professional drag racing for 3 unforgettable seasons. Next, in looking at modern Pro Stock, where engines produce over 2,500 horsepower from the same 500 cubic inches, it's easy to forget that every incremental improvement built on previous innovations. Johnson's fuel pump modifications were one crucial step in that evolution, showing that power limitations weren't always where people expected them to be. The story serves as inspiration for today's innovators. In an era of spec racing and tightly controlled regulations, finding competitive advantages becomes increasingly difficult. But as Johnson proved, they're still there, hiding in plain sight, waiting for someone with the knowledge and determination to find them. The next breakthrough might not be in exotic materials or revolutionary designs, but in recognizing and solving a limitation everyone else accepts as normal. An end today, Warren Johnson is retired from professional racing, but his influence continues through his son Kurt, who carries on the family racing tradition. The shop in Arizona, where those secret modifications were performed, still stands, a monument to innovation and competitive spirit. The modified Hilborn pumps that once gave Johnson his advantage are now collector's items, pieces of racing history that represent one man's ability to outsmart an entire sport. For anyone involved in competition, whether in racing, business, or technology, Warren Johnson's fuel pump secret offers timeless wisdom. Look where others aren't looking. Question what others accept. Test what others assume. And when you find that advantage, that edge that separates you from the competition, protect it wisely and use it well. Because in the end, races aren't won by tenths of a second. They're won by thousandths of an inch of additional fuel passage diameter that nobody thought to measure. What's the most clever racing innovation you've ever heard about? Drop a comment below and share your thoughts on whether Johnson's secret was genius engineering or unsporting advantage. If you enjoyed this deep dive into one of racing's greatest secrets, make sure to subscribe for more stories of engineering brilliance and competitive innovation. Until next time, keep questioning assumptions and remember, sometimes the biggest advantages come from the smallest modifications.